Now that we've given an overview of the structure and functionality of the ImageStreamGang app and visualized how the various stages will operate, we'll go ahead and take a look at the source code that implements the parallel streams version of the ImageStreamGang app. I'll also talk about the pros and cons of the parallel stream solution, which will help us understand how parallelism can improve things using Java 8 parallel streams, as well as foreshadow some of the discussions we'll have next when we talk about the Completable Futures implementation of the same app. Let's start by talking about how to implement parallel streams in the ImageStreamGang. As usual, we'll focus on the process stream method, which is defined in the ImageStreamParallel.java file. This is the main hook method that's used in order to be able to provide the entry point into the parallel streams processing whose source code we'll be analyzing next. We start off by getting a list of URLs by calling the getInput method. GetInput is a method that's defined by the underlying StreamGang framework, and it's used to get the input from whatever input source is relevant. For example, the input source could be the URLs that are typed into the GUI on the Android app. The list of URLs could also be provided in a command line form, or hard-coded as some kind of a test array, or even provided by some kind of input file. For the command line version, it'll be coming from one of those later sources. For the Android version, of course, this will come from the GUI that was provided by the user. In any case, we'll end up with a list of URLs. This list of URLs is then converted into a collection, from the collection format into a parallel stream format by calling the parallel stream factory method. Nothing surprising here, of course. The next thing we'll do is we'll go ahead and apply the intermediate operation filter, which is a Java 8 aggregate operation. And what we'll do here is we'll take the input, being the stream of URLs, and then we'll go ahead and remove from that stream any of the URLs that correspond to images that have previously been downloaded and cached by an earlier run of the program. As you can see, you can take a look at this. This uses a method reference called URL cached. We'll look at that implementation shortly. And you can see what we do is we negate the result of that. So if something is cached, then we negate it, and that would then turn it false, in which case it won't pass through the filter. What comes out of filter is an output stream consisting of URLs in the input stream that are not already cached. The next thing that we're going to go ahead and do is recognize that filter can return less than or equal to the number of input stream elements. Of course, in our case, if there's cached images, then it'll return less than the number of input streams. But if none of them have been cached previously, then of course we'll get them all back. So it can always return less than or equal. Here's a little view into the implementation of the URL cached method. As you can see, it's a predicate that takes in the URL and returns true or false. And internally, it uses a stream that corresponds to the list of filters that can be configured into the program. These can include things like a grayscale filter, or some kind of emboss filter, or a red eye removal filter, or a blur filter, whatever kind of filtering transforms you would want to apply or have been configured into the program. And this is basically used to determine whether the URL has already been downloaded into an image and had filters applied to it already. And so the way this works is we go through each of the filters, we turn them into a stream, and then we go ahead and filter the filter, which is kind of a funny name, kind of funny phrase, by using the intermediate operation from Java 8 streams called filter in order to be able to check whether a given image at a given URL has already been downloaded. And we do that by calling another URL cached method. We'll look at that in a second. That's a helper method that takes a URL and a file name. And if any of those things come back returning true, then they will be included in the count at the end of the stream. And so this URL cached method will return true, which means, of course, that this image has already been downloaded and filtered or transformed. So we'll ignore it and not pass it down through the stream. You can see here this helper URL cache method, which just basically checks to see if a file with a given name already exists in the file system. And if it does, the assumption is that that got put there by an earlier run of the program. So once again, we will skip the downloaded and cached images. Clearly, there are better ways to implement an image cache. This is a loose approximation of the kind of thing that you would find with the various mechanisms in a web browser to be able to cache images locally on the browser. The main difference is this implementation is pretty simple-minded, and so it doesn't try to do all the various cool things you'd get with a browser cache, where it will respect the max age of the image that's been downloaded and then re-download it again if it's become stale. We don't go to that amount of trouble for this simple test program. So coming out of the filter intermediate operation will be a list of URLs that have not yet been downloaded. So we then turn around and apply that as the input into the map intermediate operation, and we call the blocking download behavior, or actually map will call the blocking download behavior on every non-cached URL. And what we'll see as we look at this later is that blocking download will go ahead and download the non-cached image corresponding to that URL. What we get as the output of map will be an output stream that consists of the images that are downloaded from the URLs in the input stream. And always remember that map needs to return the same number of images or same number of output elements as it got as input elements. So for each of the various output elements, we'll get that will have corresponded to an input element, which in this case would be a URL that hadn't been cached. So they has to match the input and output. Here's a little snippet of what the blocking download behavior does. It downloads the content from the URL and converts it into an image. In order to do this, it uses the blocking task call and manage blocker method that we had talked about earlier in this course. We talked about this when we had discussed the way in which you can use the managed blocker interface as part of the common fork join pool. So this uses a managed blocker to ensure that there's always sufficient threads in the common fork join pool in order to be able to make progress. Now, why do we need to do this? What's the relevance of this? Well, the relevance of this, of course, is that downloading an image is an I/O-bound task. And what that means is that for a non-trivial amount of time, the image will be downloading, and so that thread of control will be blocked in whatever lower-level Java and C/operating system function does the actual downloading across the network. So that's what we would call the wait time, or the WT. And in those types of situations, we need to be careful that we have enough threads in our pool, in our worker thread pool, in the common fork join pool, so that we don't end up underutilizing the CPU. So that, of course, raises the question, how many threads should you have in general for I/O-bound tasks? And this little formula, which comes from the article described at the link at the bottom of the slide, helps give us some insight for this. So the formula basically says that I/O-bound tasks, like download image, on an N-core CPU typically run best with a certain number of threads. And the little formula we have here, which is courtesy of Brian Getz, is that it's N, which is the number of cores, times 1 plus WT divided by ST. So that's a ratio. And remember, WT is the wait time. That's basically how long an operation blocks, or how long operations block. And ST is the typical service time, which is how long things actually spend processing after they're not waiting or not blocking anymore. Now, as you can see here, if the wait time is very small, we're not spending much time blocking relative to the service time, then that value goes to essentially 0. So we end up with an equation that computes N times 1 plus some tiny number, which is basically N threads. So if wait time is low, if you have essentially a CPU-bound job, then you need about N threads. Conversely, if wait time is fairly high, in that case, WT divided by ST will be a larger number. And if wait time is actually longer than ST, we're going to end up having numbers larger than 1. So what you would end up with in that case, let's say for sake of argument that we waited twice as long as the service time was. Well, in that case, we'd end up with n times 1 plus, say, 1 or 2. So that would be 2n threads. So the longer the wait time, the larger the pool needs to be in order to keep the processor cores more fully utilized. Now again, something like downloading and processing images and reading and writing them to the file system, those are pretty much I/O-bound tasks. Conversely, when we talked about the ImageStreamGang program in the previous parts of this discussion of streams and parallel streams, those were essentially compute-bound tasks, which means that they didn't have to block on I/O. They were simply searching for phrases in strings, which were already in memory. So in that particular case, you'd end up with essentially no wait time, so you'd really need just n threads. So for compute-bound or CPU-bound tasks, then the number of threads in a pool should be essentially the same number of cores on a processor. Whereas for I/O-bound tasks, it will be typically a higher number of threads in order to be able to run effectively. What you can see here, just taking a step back and thinking more broadly about what's going on, by using the blocking task call-in manage blocker, that's a very conservative approach which essentially spawns a new thread in the common fork join pool whenever an existing computation or task would block. So that'll increase the number of threads on a temporary basis, but keep in mind that the threads in the pool can be reused, and if they're not accessed for some period of time, if they lie unused or lie fallow, as the case may be, then the fork join pool will go ahead and shut them down automatically. So that's just a little side discussion about trying to figure out the number of threads in a pool. And this is an equation, and then the fork join pool does kind of an approximation of this. What we get back from map will be an output stream that will contain all the images that have been downloaded. We then go ahead and route that into the flat map intermediate operation, passing in the apply filters behavior. And what that will do, as we'll see in a second, is that goes ahead and applies a bunch of image transformation filters, not to be confused, of course, with the intermediate operation filter that's part of Java 8 streams, but instead it'll apply an image transformation filter. In fact, multiple image transformation filters will be applied to each downloaded image in the input stream, and the results that have been transformed will be stored in the file system on the local computing device. One of the things to remember about flat map is, unlike map, it can actually return greater than, equal to, or less than the number of items in the output of flat map than comes in with the input of flat map. So in particular, the number of output stream elements might differ from the number of input stream elements. In this particular case, I believe we have 2 filters configured by default. So if we get n images coming in the input stream, we will get n times m, or 2 in this case, images coming back out as the result of flat map. It doesn't always have to be that way, of course. In some cases, flat map could do other things, but in this case, each incoming image will be filtered twice, and so we'll end up with n times 2 as the output from flat map. Here's what the apply filters behavior does. You'll notice a couple of interesting things about it. First of all, it returns a stream of images, not an image or an array of images, or an array list of images, or a list of images. It returns a stream of images. And if you take a look at the implementation, you can see that we create a parallel stream to handle all the various image transforming filters. And each of those filters is then run using the map operation against the image that was provided as a parameter. And that filter is applied using a helper method called makeFilterWithImage. And makeFilterWithImage creates a decorator object that's a filter decorator. And what it'll do is it'll go ahead and apply the filter to the image, and it'll store the results onto the underlying computing device. As you can see here, all this takes place in parallel. So for each of the filters used to transform an image, those filter operations will run in parallel using a parallel stream. Now again, the output of apply filters is a stream, and that means that FlatMap will end up essentially returning a stream of images. Now, the final thing to remember here is that nothing has been happening at this point. Even though I've been talking about getting rid of cached images, I've been talking about downloading URLs or downloading images from URLs, I've been talking about applying filters to downloaded images and storing them. None of that starts to happen until the terminal operation is reached in the stream. In this case, that's collect, which, as you recall, is a reduction operation that will combine all the elements of the stream into a single composite result, which in this case will be a list of filtered and stored images. Recall the way collect works. When collect is hit, that will trigger all the other intermediate operations in the stream, which of course, if you recall our discussion of streams internals, is built up as a linked list of these kind of stream modules that keep track of the intermediate operations. And then after collect is done, we'll create a list, or it'll accumulate internally in the collector a list of filtered and stored images, and that will be what's returned as the result of collect. So you can see that that ends up being stored here as a local variable called filtered images of type list. And the very last thing that we do here is just go ahead and log the number of images that have been downloaded, filtered, and stored, where again, filtered means transformed. Okay, so that's kind of a summary of what's going on with our ImageStreamGang parallel stream implementation. Let's now talk about the pros and cons of what we've just seen. So probably the most important pro from a high-level perspective is the fact that the parallel stream version is much faster than the sequential streams version. So you can see here I've got some output that I got from some runs of the program, and you'll see here that for larger input files, for larger images, sequential streams took about 1,300 milliseconds to run, whereas the parallel stream implementation on the same input in the same order took about 380 milliseconds. So it's not quite linear speed up, but it's a good speed up. Likewise, down below, where we're dealing with faster, or rather, sorry, smaller images, so the processing takes less time, you can see the sequential version executed in about 400 milliseconds, whereas the parallel stream version implemented in about 170 milliseconds. Once again, not really a linear speed up on my quad-core computer, but still quite respectable and demonstrating the fact that parallelism is a win. There's some other things that are worth noting here. The reason why this is a win is because the images are downloaded and processed in parallel on the multiple cores. So if I have a 4-core device, I have a 4-core phone, I have a 4-core computer, then those different cores and the different threads in the fork joint pool that underlies the parallel streams framework will actually be responsible for doing this processing in parallel. And once again, always remember that it appears as though the processing takes place from left to right, but it really takes place from top to bottom in each of the threads in the pool. And they just take turns pulling the information out of the data source through the list of intermediate operations, culminating in the terminal operation, which collects everything together in this case and creates a list of results. There's also some other benefits. The solution is actually relatively straightforward to understand, and there's a couple of different reasons for that. First, the behaviors we have, such as checking to see if something's already cached, performing the blocking download, applying the various filter transforms, and so on, those map very cleanly and very directly onto the design intent of this program, which is to ignore images that are already cached, download ones that aren't cached, and apply filters to transform and store them. And that description is almost identical to what you see here as the intermediate operations in the Java stream. Just happens to be running in parallel, but the basic point is that it's easy to understand the behavior. It's also fairly easy to understand the solution because all the behaviors that are called, so checking for the cached images, doing the downloading, applying the filters and storing and so on, all those behaviors are synchronous, which means there's kind of a request-response model from caller to callee, and it's easy to take a look at the code and just sort of understand it. And one reason why it's easy to understand it is because we can essentially do a linear read of this from top to bottom, and the flow of control just goes very nicely from top to bottom. There's no looping, there's no conditional branching, so all we have to do is just sort of understand each of the stages. And I guess I would also be remiss if I didn't point out that another nice thing about this is that each of the different operations is fairly self-contained. Interestingly enough, they're not entirely stateless. So for example, the blocking download creates a file that sits somewhere, and applying the filters goes ahead and creates files. But it's still pretty easy to read it from top to bottom, and the behavior makes sense. Unfortunately, of course, not everything is rainbows and unicorns. So there are, in fact, some cons with the Java 8 parallel stream solution. And probably the biggest con is the fact that there are faster ways to implement this behavior. And if you take a look at the performance results here, you'll see that while parallel streams are way faster than sequential streams, they're by no means the fastest way to do this processing using Java 8 frameworks, parallel computing frameworks. So you can see that we have a couple of different Completable Futures versions, and they run significantly faster than the parallel streams version. In fact, those actually are giving us essentially linear, or in some cases super linear speedups relative to the number of cores on my device that I use to run the benchmarks. So you can see that Completable Futures 2 executes in about 276 milliseconds. Completable Futures 1 executes in 285 milliseconds, which is significantly faster, almost 100 milliseconds or more faster than the parallel streams version, and super linearly faster, or close to super linearly faster than the sequential streams version. The reason why you get this super linear speed up comes down to the fact that these are hyper-threaded cores, so there's going to be some additional improvements by the core implementation being able to pipeline some of the processing. It's not a huge win, it's a little win, but it does give you good performance, as we can see here. So you might ask the question, why are Completable Futures faster than parallel streams? And I think it really has to do with this difference between synchronous and asynchronous processing. So we will cover that when we get to the Completable Futures lessons, which are coming up next. That's what we'll be covering starting next week. And what you'll discover as we go through this is a general rule, not always true, but true the bulk of the time, where there's a trade-off between computing performance and programmer productivity when choosing among these different parallelism frameworks. So as a general rule of thumb, the Completable Futures framework leads to more efficient and scalable solutions than the parallel streams approach. However, they're somewhat harder to program. The Computable Futures and the framework is somewhat harder to program than parallel streams because you have to become better versed with asynchronous processing, so-called reactive programming, and it kind of requires a little standing on your head to understand the inversions of control that are taking place. Now, the good news is that the Java 8 Completable Futures framework really simplifies a lot of this, so you don't have to wrestle with quite as much low-level detail than if you were programming with asynchronous callback models, which are really a nightmare to try to deal with because they lead to so-called callback hell. And there's also some really cool things we'll talk about where we can combine streams and Completable Futures together to kind of give us sort of the best of both worlds. You get sort of the simplicity and linear nature of programming in stages using streams, but we get the benefits of asynchronous processing with Completable Futures. So that's what we'll talk about next. But for now, at this point, you should have more than enough information to understand how to implement parallel stream solutions and how to reason about what makes them an improvement over sequential streams or more traditional ways of writing code with for each loops and conditional branches. So that's the end of this particular part of the lesson. And at this stage, we're really almost done with parallel streams coverage. We will, of course, also talk about kind of the pros and cons of parallel streams at a higher level than this. And we'll also talk about some cases when to use parallel streams and when not to use parallel streams, because they don't apply across the board in every circumstance.